I'm Ben Wandelt, talking to you from Paris currently. I wish I could be with you there right now, but I'll be back in New York in 2 weeks from now. All right, so the organizers asked me to give a review talk on simulation-based inference. My goal for this talk is mostly for everyone to get an excellent understanding of what simulation-based inference is, and then show some applications just to give you a sense of what it makes possible. All right, so I'm going to take a Bayesian point of view because I find that easier. So here's what you do, as many astrophysicists spend their time doing this. You start by working out the full physical and stochastic model of your data given parameters, or maybe you approximate that in some way. That is what you need to do in order to write down a probability density function that is the likelihood. So that's the function that you see in with the green box around here. So that's the probability density for the data given a model. So this is, when you model the data given some parameters, then you're basically writing down a likelihood. Often people will choose a Gaussian approximation for that. In fact, most of the publicly available likelihoods in cosmology, which is what I mostly spend my time on, are Gaussian approximations. Sometimes that doesn't work well, and you need to do something more detailed there. So you might have gamma distributions, inverse gamma distributions. If you have counts, then this may be Poisson distributions. And as you can tell, I'm actually mentioning some very well-known distributions, and that's because typically the need to write this down explicitly is why people choose distributions that are typically members of a well-known class of distributions. Typically in the exponential family, Gaussians, these kinds of things. Maybe exponential distributions, depending on what you have. Actually, I've just realized I'm not sharing my video. Would you like me to share the video as I'm giving the presentation?
We would like to see you, Ben, yes.
Okay. All right, now I have to find the place how to share the video. Oh, we go. Good. Hi, everyone. All right. Good. So once you've done all this work, this is what you do as a physicist. You can work out predictions for your data given your model. That's what the likelihood encodes. You then have to specify a prior if you want to do the analysis the Bayesian way. Typically, you try to choose an uninformative prior, so you might use a uniform distribution with very wide bounds, or maybe a Gaussian distribution that has a large variance, something like that. And but again, I'm mentioning well-known distributions. We'll get to the case where that may not be sufficient. So and then you get your data, and since you've done all this previous work, you've got your likelihood, you've got your prior. Now all you need to do to get your posterior is to multiply those two things together by Bayes' theorem, which I've written down there. Okay, so and then you explore this posterior for fixed data. So you have this data, okay, D, so that's now fixed, and now you explore this product of likelihood and prior as a function of the parameters. So if the number of parameters is small, it might be most efficient to just make a grid to evaluate this thing on the grid. You get a PDF, like some shape on that grid. Or if the parameters are larger numbers of dimension, typically it already starts at more than 2 or 3, then you do a Markov chain Monte Carlo. Those are the methods of choice for exploring this distribution. And of course, the end result is then a high density where the parameters, where the most probable parameters are given your data, and a low density where the least probable parameters are given your data. Okay, that's what you do this is what most people learn when they learn how to do data analysis in a Bayesian way. Okay, so there are some challenges for actually implementing this program or this method or this approach. Even when the likelihood and posterior are given explicitly, so when you can write them down, there are members of, to a good approximation, there are members of these families, then it can still be true that the computation of the posterior can be challenging. So for example, if your data involves, if generating your data or computing the likelihood as a function of your data is challenging. For example, when your data is a very nonlinear model or maybe a computational model, when you have to do a lot of computation for every parameter if you want to evaluate the likelihood for a given data set. And if the shapes of these distributions are a little bit more complicated, that makes it also hard to sample if you use Markov chain Monte Carlo. So the likelihood can be costly to evaluate. And then there's this, if you want to compare different models against one another, then there's this fourth member of the Bayesian quartet, which is the P of D, which is often called the evidence, which enters when you try to compare different models. So if you have data and you want to say, okay, what's the relative probability of two models, then you compute evidence for the for the two sets of assumptions, and you can compute the ratio of that, and then that will give you tell you which of those two models are more likely to have produced the data. But that can also be very difficult to compute because it means you have to do integrals over the parameters. So that's when life is good, in the sense of, that's when you actually have, what to write down for your prior and for the likelihood. What happens when you don't even know what the likelihood looks like? So your data are a galaxy survey. No one knows what the likelihood of a galaxy survey is, not in closed form in any case. Or your data, even if your signal is simple, so for the cosmic microwave background is the standard example of a very simple signal where it's just an extremely good approximation. It's a Gaussian with some covariance. But even there, the noise is very complicated. So you have a galaxy foregrounds, dust emission, very non-Gaussian, and very complicated to model, and no one knows how to write down a good likelihood for that. And in fact, there may be cases where the prior is also not well known. So, for example, if you have data, or if your generative model is a GAN, so we live in the age of the deep learning revolution. So if you're generating your data from a model that you don't have really analytical understanding of, it will generate you some types of signal, but you don't really know what the distribution is of that. And then so even the prior may be unknown or intractable. So the obvious question to ask is there another way? And the holy grail would be if we could just say that, if you can simulate your data or you can generate your data in some way, then that's all you need to analyze it. And in fact, yes, there is another way that helps us approach that goal. And so let's do a very simple example of that. So this 2D diagram here is, in my opinion, is the best diagram to explain Bayesian statistics. So even if you're not interested in simulation-based analysis, if you're just interested in understanding Bayesian statistics, this is extremely clear and illuminating. And basically, it's what I always have in mind when I think about Bayesian anything. All right, so what we have here is just a diagram with it's just 2D. I'm dealing with a case where we have one parameter and a one-dimensional data set. Okay, I realize that that's a simple case, but it's very helpful for visualizing the two together in this 2D plot. Okay, so and And so what do we do? So let's say we have, I told you we have to somehow specify a prior, but actually all we need to do is to be able to generate parameter sets, or, so theta could be parameters, could also be signal, and the data is a noisy version of that signal, for example. But okay, let's say what theta is a parameter here. And I'm going to generate examples of that from my prior. So, so I'm generating lots of thetas, and I'm just putting a line at every theta here, these yellow lines. Great. So now, since I've, and now all I have to be able to do is, for a given set of theta, I have to be able to generate some data. So that, if I can do that, and I get this, okay, this is for a particular model. I don't need to go into the details. It's just one particular model that I'm choosing here for the illustration. Okay, so I haven't drawn in all the thetas, because then this would basically be just a yellow box. Just for some, I've drawn thetas for some subset of those, but let's say at every theta here that I've drawn, I can just generate a d given theta, and that will the d will lie on a vertical bar like that. So this is, that gives me this set of blue points. And so that set of blue points, since I've now drawn from P of theta, and then I've drawn from P of d given theta, from the likelihood, that chain of two draws gives me samples from the joint distribution of theta and d. And that's really the fundamental object in Bayesian analysis. So here we've done that, and notice that we never needed to evaluate any probability densities. We didn't have to write down anything. We just had to, I'm going to switch off my my speakers because I'm getting some echo. All right. So we never had to write down anything. All we had to do is we had to be able to draw from theta, and we had to to generate d for any given theta. All right, now we have this joint thing. Now we go and actually measure our data. So our data is going to be some value of d. So I'm putting a horizontal line at whatever that happens to be. Okay, here's our measurement. Okay, now let's do inference. All we now need to do is to slice through this diagram. Remember, this is the joint distribution P of theta and d. And so a slice through that at a given d is going to be proportional to P of theta given d, to the conditional distribution, which is the posterior, which is what we want when we do Bayesian inference. All right, so if I take an infinitely thin slice like this, I'm not going to capture many points. So I'm going to make a slight approximation and just take a finite width slice. So I slice through this joint distribution at or around the value of my measured data. So in stats parlance, I'm conditioning on the data. So I only allow points in the space of data and parameters that are consistent with the actual data that I've obtained. Okay, now I find all the points from my simulations, these points that satisfy that, so that are within this range. Now, of course, I could have chosen a different epsilon. If I'd made it wider, I would have gotten more points. But you can see that they would be quite, they would get spread further and further. If I made the epsilon smaller, then I would get fewer points, but in a tighter range. For example, that point over there wouldn't have been included if I'd made epsilon slightly smaller. Okay, but let's say for this epsilon, we get that. All right, now all I have to do is just take those points, make a histogram. Oh, by the way, yeah, so here's, in real life, you don't know this, but since I simulated it, I can reveal that the true theta I use, the true parameters I use to generate this data point, is this value here, a half. Okay, so that's kind of illustrates that the points that I selected here do cover this true theta value very well. And so if I just histogram these points, then I get this, and the true theta value again is in the black bar. So this is now an approximation to the posterior, so it's slightly too wide because I had to choose a finite width here, but that's only going to make it a little bit conservative. In this 1D example, it's actually quite a good approximation. So if I could make this epsilon very small, so if I had more simulations, I could capture enough points here to still draw a diagram like this, get a good estimate of the posterior, then I could get a slightly sharper version of this. And this is really all there is to it. Okay, this is the essence of simulation-based inference. Everything else that we're going to talk about from now on is basically engineering. There's a bit more conceptual stuff, which translates maybe to some more general problems. But now we're just going to talk about how to make this possible when you have more than one parameter, or when you have more than just a single number as your data set. All right, so all of this relied on the fact that simulated data, so you say simulation, that's nothing other than a draw from the likelihood that corresponds to the code that you're using to simulate. Okay, so if you're doing simulation-based inference, then essentially your likelihood is implied by whatever computer code you write to generate data, generate the data simulation given a set of parameters. Right, that's shown down here. And then that means you don't actually need the likelihood anymore to, you don't need to evaluate that thing anymore. It's just that you just represent it through these simulations. And as I just showed you, that means you can now do inference. So I actually prefer the term implicit inference for that reason, because implicit inference is a class of techniques for building inference engines when the explicit likelihood or prior form is unknown, or maybe if it is known, it's super hard to compute. But you can generate theta, like parameter data pairs or signal data pairs, either through simulations or some other generative prescription. And in that case, the likelihood or the prior, actually also, are not explicitly specified as probability densities, but are implicit in that prescription, whatever it may be. So it could be a simulation code. Now it could also be a neural generator, like I mentioned earlier, or it can actually be labeled observations. So sometimes you may even have actual real data, and for some reason in those cases you actually know what your parameters or what your true signal is. And so when you have labeled data parameter pairs, you can even use real data. You can even have humans in the loop, right? I mean, if you have enough time and you can generate data, have humans in the loop that generate your data, you could even simulate, include all of that. So this is more general as a concept than simulation-based inference, but simulation-based inference is, well, probably the best known example of that. There are other words that are used for this. So likelihood-free inference, that doesn't include the case where the prior is difficult. And of course, it's not really likelihood-free because the likelihood is still there. It's just implicit in your in your generative prescription. Simulation-based inference if you're using computer simulations, but it could be something else. And approximate Bayesian computation is also sometimes used synonymously with this, even though it's really just a very simple algorithm for implementing it. In fact, it's the algorithm I just showed you, okay, where you generate and then you slice through, but you have to put an epsilon so that you capture some, you actually capture some points, and then you don't miss all the points because you do an infinitely thin slice. And in cosmology, for example, which was probably the earliest, the part of astrophysics that was adopted this first, this was used for image analysis and weak lensing, and they were using approximate Bayesian computation. And so the way that they were checking whether the data satisfies the epsilon constraint there was pretty lossy, so very permissive, because to actually get a few accepted points. So it wasn't, it was kind of more a desperate measure than a method of choice, let's put it this way. But things have changed. So here's another example. I'm going to may skip this and just go through very quickly. It's just it's sort of an algorithmic way of showing a similar example to what I already showed you. So the approach is you draw off some parameters from your prior, you then simulate. You typically extract some summaries from your simulations, so illustrated by these red points. You have the same summaries computed on your data. You then check according to some distance whether the simulated data are equal to or similar enough to the actual data within some epsilon. If yes, you accept the parameters you used to simulate. If not, you reject the parameters and you just start over. And in the limit of epsilon going to 0, then the remaining accepted parameter samples are samples from your posterior, and you can do your inference. All right, so that basically concludes the explanation of how you can do inference when all you can do is simulate or generate your data and you don't have an explicit model. Now let's talk about actually making it work so that it's not just a desperate measure, but it's actually, it turns out in some cases now this is simpler. Even when you could do the explicit version, this is more efficient. The difficulty here is that the simple version, the approximate Bayesian computation, ABC, becomes exponentially difficult when the data dimension is high, because you have to then only keep data points that are very close to the simulations that are very close to your data. And in high dimensions, everything is far away. So it's very difficult to ever hit close to the data with your simulations. So that's called the curse of dimensionality. It's a very good example of that. And so either you need to do dimensional reduction or you need to find smarter approaches of doing this. So this dimensional reduction also is called summarizing, and that's what people often do in any case when they take data. You don't use the raw data, but somehow you compress it to some quantities that may be meaningful to you or are just chosen to be informative about your parameters in some way. Most of the time, these summaries are human chosen, but there are now actually many examples of automatically generated summaries. And I'll talk about how to do that in a minute. And the approach again is you take your data, you compress it to those summaries. You then do your sampling of theta and parameter and data pairs. You compress those the same way. Then you have simulation summaries. You combine them together to get your posteriors. So this because the summaries are lower dimensional, this is much more feasible. But then what you do here to actually turn this into a posterior is there are a number of different choices. And the particular choice I showed before, ABC, can work as long as the summaries are in low enough dimension, but there are now more powerful alternatives. So for example, something called density estimation likelihood-free inference, or Delphi, what it does is it actually learns the likelihood. So when you go, actually go back to this example. So here are my samples from the joint distribution theta and d. You can now slice this in multiple different ways. So for example, you could take these simulations and actually learn a model just from looking at this, at various theta slices. You can learn probability densities at every theta. In fact, you can tie them together and just learn probability densities as a function of theta, which is you're learning the likelihood, and you're learning a density. Doing density estimation on these samples. So that's why it's called density estimation likelihood-free inference. Sorry for this. This has really been enabled by having very efficient and powerful and expressive neural density estimators. So either using, for example, neural mixture density estimators or something called normalizing flows that are conditioned on the parameter. So at every parameter, it gives you a way of modeling your data distribution, and you can learn it from these examples that you can generate. Another approach is called likelihood ratio estimation. So that's also a way to learn the likelihood, but now as a way to evaluate the likelihood as a function of the data, if you prefer that. So here's some references for for papers introducing this. The earliest version of likelihood ratio estimation are now almost historical. The neural density estimation approach was pioneered by Makarios and Murray, and we have an implementation of that that's that we've built in the context of cosmological problems. And then there is an evolution of this likelihood ratio estimation called truncated likelihood ratio estimation in these more recent papers. So there, I talked about getting the number of the data dimension down, but sometimes when you have very large numbers of parameters, it can also make it hard. So it turns out if a lot of those parameters are nuisance parameters, so maybe you're not that interested in them, but they're just in your model to kind of absorb various nuisance effects. It turns out you can be quite permissive in the number of nuisance parameters because they can be dealt with in an approximate way, and you can harden your summaries against these nuisances to make that everything much more efficient. So this is one more point I wanted to mention. And this here's our PyDelphi code again that implements these conditional neural density estimators. There's another very widely used package, SBI, which which has a number of different techniques, including likelihood ratio estimation and neural density estimators. I think using ensembles is quite important. We found that makes things much more robust, which I think here you have to do kind of manually, but that's kind of the default in PyDelphi. Anyway, these are small differences. So then there's already some machine learning in what I mentioned, these neural density estimators, and so these flexible models for with various probability densities that occur for finding good summaries. But I'll talk more generally about, in the remaining minutes, about using neural computation and the ability of neural computation to optimize complicated objective functions in what seems like, they sort of seem to make it easy. It turns out that in some cases we can turn what looks like hard inference problems to optimization problems and solve them just by training a neural network. So let me show you what that approach entails. So the key thing when you want to convert an inference problems, sorry for the typo here, converting inference problems into a neural optimization problem, is that you write down a loss that defines the problem you want to solve. Then you parameterize the solution to the problem using a neural network. You run your favorite optimizer, Adam, or whatever it may be, stochastic gradient descent, and then you validate the solution. So first example, let's do variational Bayes. So let's say you have a parameterized family of distributions. Okay, so this could be a neural density estimator, and that gives you Delphi. So that's a probability distribution here for the data summaries given a parameter set theta, and the W represents the weights or the parameters of your family of distributions. So this could be, the weights and biases of your network that computes the neural density estimator. And you can then train this by minimizing the Kalbeck-Leibler divergence between this approximate distribution and the true distribution, where the true distribution is represented by your simulations. You can then get a finite sample approximation to this Kalbeck-Leibler loss, and by changing the weights, you can then get a density, the optimal density out, and you can then use that to do your inference. So let me show you an example based on gravitational lensing data. So strong lensing. Here's some simulated images. That's your data. So it's noisy, and you can see quite complicated. And when you do this scheme that I just mentioned, in this case, this is done using the PyDelphi package. The red contours here show the resulting posteriors that you get out. The blue is an alternative method that it's called Bayesian neural networks, which follows a different approach, which I won't cover here. you can get, quite high dimensional posteriors. You can see all these, every single line here and every column is a parameter. So this works very well even on this problem. And how do I know that it works well? Because we can then validate it. So here we have an observation, like simulated observation, the true lens, the true source. So this is a case where both the source and the lens are being inferred simultaneously. This is trained on forward simulations of lensed data for all kinds of sources, all kinds of lenses, and all kinds of configurations. So you can then do tests like as a function of your parameter, you can look at whether the inferred posterior probabilities actually correspond to the probability of the parameter having this value. And so for this Delphi example, which is this orange line, it's basically perfect or very close to perfect. The perfection here is shown by the dashed line. Okay. So what if you wanted to do asymptotic analysis? So let's say you don't really care that much about the shape of the posterior, or you just, you're quite happy just to have a covariance. You have a lot of data and you just want to get a covariance of your parameters using, you'd use a Fisher matrix if you knew what the likelihood was, but you don't know what the likelihood is, for example. It turns out, again, you can just write down another loss function. So view of the time, let's not go through the detailed argument here, but by writing down a loss function that is the log determinant of the Fisher matrix of the network output. So this is a stand-in for the Shannon information in the network output. So by maximizing this log determinant or minimizing the loss, which is minus that, you can then get the network to compute maximally informative summaries. And you can then, it even gives you like a pseudo maximum likelihood estimator and the Fisher matrix, so you can put error bars on it. Or you can then use those summaries, for example, in the context of density estimation likelihood for inference to do your full inference. So there's a paper about this here. We've applied this for an example. We've applied this to field-based inference, where let's say you take a Gaussian field with some power spectrum. Power spectrum depends on some parameters. You can then get the posteriors for those parameters for any given power spectrum, and all of this is just trained using the loss I just showed you, this information loss. And there's a lot of detail about this in this paper, showing how to, and this is showing both the ABC approach in terms of the points, and then also the Delphi approach in terms of the contours. In this particular case, the example can be solved explicitly, so we know what the information is, and we see as you solve this optimization problem, the loss that we're minimizing, the information loss, actually approaches the optimum as it goes forward. And it's very quick. It takes about 11 minutes, certainly longer than to derive the actual Fisher matrix for a general case. So then this was for a Gaussian case where it actually doesn't take that long to derive the exact result, but for a non-Gaussian case, which is shown here, so this is for a log normal distribution. Here are 4 different generated fields, and we can do this analysis. And if you want to follow this, go into there's an interactive notebook that shows you how to do all the steps for doing this analysis, going from a field of non-Gaussian data to parameter constraints. You can then push this further, and instead of talking about fields, you can talk about graphs. It's just another way of representing the data. So Paco has done a lot of work on using graphs for extracting information as well. And again, you can do compute Fisher information based on graphs using these techniques, using these optimization techniques, and do so. What the data objects are doesn't matter. You might not have thought of computing Fisher information for a graph, but this can do it. As long as you can stick something into a neural network, you can use this method to compute the Fisher information and the Fisher score, which is the thing that contains all that information. Okay, so finishing up, if you're going to a regime where the number of parameters is very large, so let's say you don't really care about the detailed shapes of your posteriors, you're mostly interested in just what is the, what is the value of my the parameter, and I want an error estimate. It turns out that that simplifies things quite a lot. Again, you can write down a loss function that when you train a network gives you back that number, and that allows you to go to very large dimensional problems, because then you're just solving the problem for all the different parameters kind of separately. So these are, we call these moment networks, and the detail is in this paper here. So it's a very simple loss. It turns out it's just a squared loss that if you train this, then the network gets trained to give you back the mean of your posterior for those parameters, for whatever parameter you want. And you can do a kind of double squared loss, quartic loss, that gives you the variance of the parameter. And if you do want to know the likelihood shapes of the marginals, you can also just skip directly to the marginals. You don't need to do the full density estimation in the full parameter space. You can just go to the 1 or 2D marginals so we also include that in this paper. But this, just getting the mean and the variance, is kind of the simplest form of simulation-based inference you can imagine. And this solves the curse of dimensionality because it just skips directly to the marginals. So here's an example where we applied this to the CAMELS data, and Paco has now many papers using moment networks to extract information. In the CAMELS collaboration, many authors that are doing this. For example, on this CAMELS multi-field data set, where we have 2D slices and corresponding parameter combinations. These slices correspond to various outputs of your hydro simulations, including things that, as a cosmologist, you didn't think that you'd be doing careful Bayesian analysis of. So magnetic fields, metallicity, all kinds of things. When you so again, here's this loss function. So here's the quadratic loss. Here's the quartic loss for the variance. And we combine, since we have 6 parameters and 6 variances, we combine them together by adding the logs of these losses, which helps a lot. And then you get parameter estimates out for the simulated ones. These are the against the inferred ones, and it works very well. This is from the gas metallicity. Turns out from the simulation, in the simulations, you can infer omega matter from gas metallicity slices. So we skip this robustness story. There are certain combinations that work well, even though the two different simulators are quite different. That depends on selecting the data carefully. This has also been done by Lucia on semi-analytic galaxy formation models, where it also works. This is a validation test showing that things are distributed kind of with the right mean. The means and variances work out well. Here's an example of these moment networks, now in a very high dimensional case where every pixel in this image is a parameter. You can do foreground cleaning for B modes in cosmology. You get these are hundreds of thousands of pixels and their corresponding variances, posterior means and variances. And this is, once you've trained the network, it's just in a single forward pass. And again, this validates it. And again, this isn't even published, but it was just a couple of hours work. Once you have an n-body simulation, for example, you could take the initial conditions, take the final output, and just train these networks to give you the reconstructions of the initial conditions and the variance per pixel. This is from 2D slices, because that was possible in just an afternoon. But it gives you a sense of how flexible these methods are. That's the reason why you get quite a blurry reconstruction. If you do this in 3D, it's expected to be much more detailed, because you then have all the neighboring information to help. But yeah, this is just showing, I mean, to do this in an explicit likelihood approach, I mean, we've done this a long time ago, but it took a lot of work to implement with Markov chain Monte Carlo. And okay, there's one more thing I wanted to mention, which is that you can also do this, you can also use simulation-based inference for second-level inference, meaning if you have multiple models, you can compute the evidence that allows you to compare the models. So like I said, mentioned earlier, the evidence can be hard to compute, this P of D, and it turns out that you can just write down classifiers, inspired by it can be inspired by classifiers, certain losses that you can train. So the network, when you, for example, you train with this loss here, you can get a network that returns to you the Bayes factor, which means the log of the posterior model probabilities, or rather the evidence ratio in this particular case, for the two models that you're comparing. So this is in prep, should be coming out very shortly. Here's an example of that. And the cool thing about that is that there's at no point anywhere in this do I make reference to the parameters. So if you have, even if you have 1 million parameters, this works just as well as if you have one, which is a major advantage compared to the standard ways of doing this. Okay, and that concludes my talk. I'll let you read this. Oh, I want to emphasize the last point on this, which I didn't get to because I was trying to be mostly pedagogical, which is that these methods have obviously also already been applied to real data, and in particular in the cosmology context, there's the SIMBIG results, which have done a first application of these ideas to estimating the parameters from the power spectrum of the Sloan data, Sloan Galaxy Survey, or part of the Sloan Galaxy Survey. So yeah, happy to take questions if there's time.
Thank you, Ben. Any question for Ben?
And I now realize that I had my speaker switched off throughout. So if you were trying to get me to stop, I apologize.
Yes, no, thank you, Ben. There is a question from Aritra.
Hello, Ben. Thank you for the talk. I had a question about the fidelity of simulators when we are using likelihood-free inference. In the sense, do the simulations need to be perfect, very good, or okay? Because if I understand, for example, just normal Bayesian statistics correctly, one of the things is I don't know that if I have some model, I somehow have to take into account the fact that the model or simulator I have may not be a perfect replication of the data. So how to do that when we might have maybe we are not sure how good our simulators are in the first place? Yeah,
no, this is an important question for practical applications. But so the first answer I have is that you can now, what I've talked about is that you can now confront data and models in an extremely fine-grained way. So that wasn't true before these techniques became available, developed these techniques, but now you can, and that means that now having the model, the problem is, some people sometimes say the problem with computers is that they do exactly what you tell them to do. Sometimes you want them to do what you intend them to do. So here's the same thing. We have a model. We're confronting that model that's implied by your simulation code against the data, and if the model is wrong, your results will be wrong. That's clear. So then there are aspects of this, which again, in a longer format, I would be happy to, there's very important aspects to this, which relate to the ability to mask data. So typically the way we deal with this problem in standard analysis is we mask certain aspects of the data because where we think our models aren't good enough. But we're limited in terms of how we can mask because, we have to stay within the realms of likelihood assumptions. So for example, certain kinds of masking will almost certainly make the likelihood very non-Gaussian. Whereas here, we don't really care because the likelihood is just implicit by our simulation code, so we mask any way we want, even in ways that are nonlinear in the data, and we still get valid analyses. So so there's actually much more flexibility here in terms of making much more fine-grained cuts to the data that at the same time, let information through, but reject aspects of the data that you're not confident in modeling. Now, the hard bits are the ones where, the aspects of the data where that you're not even aware that your simulations aren't modeling well. Now you can go, of course, to summaries and hope that those summaries are not particularly sensitive to that. But I would say there's no general solution to this. It's just like there's no general solution to the problem of how do I get great results if I have a really bad model. So, then really the solution is to improve the model, make more careful cuts, so that once you cut the data, and you apply the same cuts to your simulations, the simulations become good representations of your data.
Hey Ben, it's Mark. Thank you for the talk.
Hey, Mark.
Just a simple question, I think. So when you use your neural density estimator, in fact, you can choose to model either the likelihood or the posterior directly or the joint distribution as the neural density estimator. So, when, and can you recommend when it's, if there's one approach that is better than the other, and in which situations you should choose one or the other?
Yeah, very good. So let's say you're in a situation where each simulation is really costly. So you might, the likelihood evaluating, you don't have the likelihood, so that's intractable. But now you can simulate, so that's great. But maybe each simulation may still be costly. In that case, you want to minimize the number of simulations you have to run to get to an answer. And in that case, typically it's efficient to concentrate the simulations on parameters, concentrate your CPU time basically on parameters that are consistent with the data. That means doing active learning. And the most convenient way to do that, it's easier to do that when you're learning the likelihood, because you can choose what thetas to run your simulations at. There are other situations, for example, in this strong lensing example that I showed, where you have a ton of data and you want posteriors for many, many, many data instances. In that case, it can be more efficient to just train a network to give you the posterior directly as a function of the data. So go directly to the posterior, because then you stick in a data set, you just do one forward pass through the network and you get the posterior immediately. No sampling required, nothing. It just goes straight through. You then get a density estimator that you can sample from. So, but there's no Markov chain sampling. So this is called the amortized case. That's when you go directly to the posterior. Going to the joint is a little bit more, the joint distribution is more involved, but has the advantage of, let's say if you don't know explicitly what your prior is, that, I gave some examples where that may be the case, you can then project that onto the prior, or you can, also implicitly, if you project onto the data, you immediately get the evidence. So there, if you're interested in discovering more about the evidence or about the prior as a function of the data or the parameters, respectively, then doing the joint fitting may be a good option, but that's going to be the most computationally intensive.
Thanks.
Do you want to unmute and ask your question?
Hello, were you asking me?
Hi, Wandelt.
Yeah. So I had a question online. I was really interested in the parameter scalability that Benjamin just mentioned at the very end. that the computation demand from does not significantly increase with the number of parameters, which is, you know, usually a big problem for MCMC. So I was wondering if you can talk a little bit more about that. Is that like tested for a specific problem or more like a generic rule?
So this is particularly true for the evidence calculation that I mentioned, because if you actually think about evidence for a little while, and you discover that really in order to calculate evidence, you don't really need to make any reference to parameters whatsoever. And while most of the current techniques for evaluating evidence, like nested sampling, actually work with you know, in the posterior space. So they actually do posterior sampling at some level to get to the evidence. So if you have very complicated posteriors or very high dimensional posteriors, then that can be extremely intensive, whereas you don't really need that to do evidence calculation. Now, it is true that I'm not claiming that you can compute evidence for every single situation with this in a way that is easy, because there will be some complicated situations, and the main conceptual point to take away from this is that the evidence really doesn't necessarily care about the complexity of your posterior. But it is true that if the evidence as a function of the data is complicated, then that will you can still have hard problems. So it may still be hard for the neural network to actually capture the full shape of the evidence. But it doesn't. But the number of parameters doesn't really matter. Like you can, I mean, the trivial example is I can always introduce 5 million parameters that do nothing to your model. Now it's true that a you know, Markov chain Monte Carlo, depending on how you write it, might get very confused. But it shouldn't really matter to computing the evidence, because the evidence doesn't change when you just add more parameters that don't do anything. And you know, for example, in a very noisy situation, if you have a lot of structure in your posterior, that might be difficult to reconstruct. But if your data are noisy, then the predictive distribution becomes very smooth, and that actually becomes a very simple problem. So I think these techniques just give new ways of thinking about the problem. And so I don't think I can make any very general statements, but there are certainly classes of problems that become much easier. And you know, there's nothing intrinsic about the evidence problem that depends on the number of parameters. It's just the complexity of the predictive density of the data that matters in that particular case, which doesn't involve the parameters.
Yeah. Okay, got it. Thank you very much.
All right, no problem.
Any last minute? John?
Ben, really, thanks for the nice pedagogical overview. You mentioned at one point that sometimes it's more efficient to use SBI than standard MCMC, even if you have the likelihood. And I was wondering if you have a favorite rule of thumb for when you would switch between one and the other.
So I mean, sometimes the likelihood takes a long time to evaluate. So this may be the case. So let's say even if you have a Gaussian likelihood, but your covariance depends on the parameters, then you have to you have to compute the covariance, the determinant of the covariance matrix at every likelihood evaluation, and that can quickly become intensive when your data vector is high dimensional. Whereas simulating Gaussians, for example, is typically can be done much more quickly. That's one example. Just in general, there's Markov chain Monte Carlo is inherently sequential. I mean, I know you can run multiple chains in parallel, but they all have to get through burn-in. Then once they're all burned in, yes, then you get the parallelization happening. But here, generating your training set can be done in advance for a lot of these problems. So then it's completely parallel. So if you just run lots and lots of simulations in parallel, then you can really take advantage of parallel architectures, and that can just reduce the wall clock time to the result by a large factor. Now, I did mention these adaptive learning techniques. So they, you know, you're doing adaptive learning, then there is some sequential, like you're running some simulations, then you're deciding where to run your next batch of simulations, etc. So it's not completely parallel, but you can, each batch may still be hundreds of simulations that you can do in parallel. So that high degree of parallelism is something that can really help.